What specific problem does your proposed method of chroma teaming and model editing aim to solve in the context of LLM vulnerabilities?
The proposed method of chroma teaming aims to address the vulnerabilities of large language models, LLMs, by fostering collaboration among various security teams, red, blue, green, and purple, to enhance the overall resilience of LLMs against adversarial attacks. Specifically, red teams identify vulnerabilities through simulated cyber attacks, while blue teams focus on defense strategies. This collaborative approach allows for a comprehensive understanding of potential threats and the development of effective mitigation strategies. On the other hand, model editing seeks to improve LLM behavior by modifying architecture, parameters, or weights to correct undesirable outputs without complete retraining. Together, these methods aim to fortify LLMs against a range of adversarial threats, ensuring safer deployment in real-world applications.
How does your proposed method or algorithm work? Illustrate it step by step, particularly focusing on the mechanisms of both chroma teaming and model editing.
The proposed methods, chroma teaming and model editing, work through distinct yet complementary mechanisms to enhance the security and resilience of large language models, LLMs. 1. Chroma teaming involves the collaboration of various specialized teams, red, blue, green, and purple, each focusing on different aspects of LLM security. Red teams simulate attacks to identify vulnerabilities, while blue teams develop defenses. Green teams explore beneficial uses of potentially unsafe content, and purple teams assess the cybersecurity safety of LLMs by combining insights from both red and blue approaches. This collaborative synergy aims to create a comprehensive defense strategy against adversarial attacks. 2. Model editing refers to modifying the architecture, parameters, or weights of LLMs to improve their behavior and robustness. Techniques such as gradient editing, weight editing, and memory-based editing are employed. For instance, gradient editing uses model editor networks with gradient decomposition, MEND, to adjust gradients, ensuring that local edits do not negatively impact overall performance. Weight editing, exemplified by Rank 1 model editing, ROME, focuses on modifying specific weights to enhance factual recall, while memory-based editing incorporates external memory to update model behavior effectively. Together, these methods provide a structured approach to fortifying LLMs against vulnerabilities, ensuring they can operate securely in real-world applications.
What are the theoretical or practical benefits of your approach in addressing LLM vulnerabilities compared to existing strategies?
The theoretical and practical benefits of our approach, particularly through chroma teaming and model editing, lie in their comprehensive and collaborative nature in addressing LLM vulnerabilities. Chroma teaming unites various security strategies, red, blue, green, and purple teaming, allowing for a multifaceted defense against adversarial attacks, which enhances overall resilience compared to traditional singular approaches. This synergy enables the identification of vulnerabilities while simultaneously safeguarding against threats and exploring innovative solutions. Additionally, model editing techniques, such as gradient and weight editing, provide targeted modifications to LLMs without the need for complete retraining, thus improving model behavior and robustness efficiently. Together, these strategies not only address existing vulnerabilities, but also pave the way for future advancements in LLM security, making them more adaptable and effective in real-world applications.
Can you detail the experimental design and datasets used to validate your proposed methods? What metrics did you utilize to demonstrate their effectiveness?
The paper does not provide specific details on the experimental design or datasets used to validate the proposed methods of model editing and chroma teaming. However, it mentions that various model editing techniques, such as gradient editing and weight editing, were evaluated on datasets like ZSRE question answering, fever fact-checking, and Wikitext generation. The effectiveness of these methods was assessed through metrics related to the model's performance on these tasks, focusing on their ability to maintain integrity while correcting undesirable behaviors. Additionally, the paper highlights the importance of evaluating model editing techniques across different layers and parameters, suggesting a comprehensive approach to measure their impact on LLM performance. Overall, while specific metrics are not explicitly stated, the emphasis on performance evaluation indicates a focus on accuracy and robustness in the context of adversarial attacks.
What were the specific results achieved with the application of chroma teaming and model editing? How did these results compare to previous methods?
The application of chroma teaming and model editing yielded significant advancements in enhancing the security and resilience of large language models, LLMs, against adversarial attacks. Chroma teaming, which integrates the collaborative efforts of red, blue, green, and purple teams, effectively identifies vulnerabilities, safeguards against threats, and generates innovative solutions, thereby creating a more robust defense mechanism compared to traditional methods that often focused on singular approaches. Model editing techniques, such as gradient editing and weight editing, demonstrated superior performance in modifying LLM behaviors without necessitating complete retraining, allowing for targeted corrections of undesirable outputs while preserving overall model integrity. For instance, the model editor networks with gradient decomposition, MEND, surpassed previous editing methods in terms of the degree of modification achieved on large transformer models. Overall, these strategies not only improved the adaptability and effectiveness of LLMs in mitigating vulnerabilities, but also highlighted the need for ongoing research to refine these methods further.
What limitations or drawbacks did you identify in your proposed approach or in the current mitigation strategies discussed? How might these be addressed in future research?
The paper identifies several limitations in the current mitigation strategies for LLM vulnerabilities, particularly in their effectiveness and adaptability. For instance, while model editing techniques like gradient and weight editing show promise, they often require access to model parameters, which is not feasible for black box models. Additionally, existing strategies may not adequately address the evolving nature of adversarial attacks, as highlighted by the dynamic tactics used in jailbreaking and prompt injection. Future research could focus on developing automated systems to reduce human dependency in color teaming, exploring model editing across diverse datasets and model aspects, and creating unified platforms to test multiple editing methods. By addressing these gaps, researchers can enhance the resilience of LLMs against emerging threats.